Okay, so for legal reasons, the very first thing I'm going to say is we are recording. Y'all may have noticed I have a YouTube channel where I post all of my lecture recordings. The idea is to give y'all a means to look back and revisit, re-experience the lecture after having done some studying. So hopefully you can get more out of it. And I talked about that at length in the recording that y'all already watched. But because I am recording, again, it's possible if you ask a question or something, even though I think the microphone's pretty local, still your voice might get picked up, so you've been informed. Okay. All right, so I'm not going to go through all of this stuff again. Y'all have already watched that video. I hope y'all have already watched that video that I made where I talked about various procedures and policies and advice on how to do well in the... Whoa, I just hit the wrong button there. How to do well in the course. So all I'm going to repeat is the importance of this part right here. Cannot emphasize this enough. You can't approach this course like a lot of the courses that I saw in high school when I was in high school that were memorize, rehearse, execute, just regurgitation kinds of things. It's just not what this course is about. It's not just that you won't be able to do the memorizing and regurgitating. It's that's literally not what you're being tested on, right? So please take this part super seriously. Very, very important to come at this course in the right way. Try to understand ideas. That's ultimately the goal. Every exam question that you will face has a purpose, which is to see the extent, to try to measure in some sense to what extent you understand the ideas and the reasoning in the course. And of course, yes, there will be formulas to know. Yes, there will be algorithms to execute. Of course, that's obvious. But this is the point. Okay, so enough of that. Let me go on to a little bit of math. Before we get into the actual course content, I want to try to persuade you that this is useful, that you should be here, right? I mean, so, why are you taking this course, aside from the obvious, because your major requires it in most cases, right? So why does your major require it? Well, I'm going to start from the assumption that y'all have already bought into this idea, that single variable calculus is important. Calc 1 and 2 classes are chock full of various applications where you can use calculus to solve problems that otherwise you can't. There's no way, right? So bonkers useful. And in a couple of ways, specifically, derivatives and integrals, right? But derivatives because they are a way of getting your hands on the idea of how things change. And that's a lot of things, right? The world is a changing place. Very little just kind of sits there, right? And then also integrals. Now, why are we interested in integrals? And this is very commonly misunderstood. A lot of people think integrals are about area under the curve. No, not at all. Well, ever so slightly, right? Really, why we care about integrals. Now, let me say that a little differently. The reason that people who are interested in applications care about integrals is very little to do with area under the curve. It's about understanding what I like to call accumulating quantities. And so there are many accumulating quantities, the kinds of stuff that you can chop up into little pieces and add up with an integral. And again, in Calc 2 classes, you saw a million examples of those kinds of things. That's why we care about integrals. So, right, fine, cool. So why isn't that good enough? Why can't we just stop with single variable calculus, right? You got derivatives and integrals, done, right? Well, what's the problem? Well, the problem is that the world is three-dimensional, not one-dimensional. In fact, even that's an understatement. If only because of the fact that the world is three-dimensional, not one-dimensional. We need multivariable calculus, but we also need multivariable calculus for many more reasons even than that. Right, so just some easy, low-hanging fruit examples of how the three-dimensionality of the world makes single variable calculus insufficient. let's suppose you have temperature in, let's say, this room, three-dimensional room. Temperature is different over there than it is over there. Maybe not a lot, but a little bit. And you might conceivably be at some point and moving with some velocity. And as you move through this room where the temperature is not constant, the temperature will be changing. So based on your velocity, which could be that way, it could be that way, it could be that way, it could be at some angle, right? There's a million different directions that you could go based on your velocity, direction, and speed. How fast is the temperature changing? Well, it's complicated because it's not like you can just say, well, temperature is a function of x, and we'll look at how fast x is changing and stuff like that. There's three different directions. You're not moving in the x direction. Certainly not exclusively, maybe, one of the components. But so how do you get your hands on the fact that the input changes that go into the temperature function are three-dimensional? Single variable calculus does not do a good job answering this question. Right? So this is one of the things that we're going to address with multivariable. So likewise, y'all have computed mass in single variable calculus. Typically it's a one-dimensional rod or something like that, or it's something where you can slice it and every slice has a constant density, and so you just say density is, density times volume gives you mass, and then you add up, right? So, okay, well, what if, as is very physical, right? I mean, the real world tends to be complicated like this. Density won't just be a function of a single variable most of the time. Most of the time, it's lumpy. You got a that's more dense kind of in this general vicinity. Less dense above, less dense below, less dense on the sides. It's lumpy and splotchy. So it's a function of three variables. How would you compute the mass here? Well, you can't just take slices, because on each slice, density is not constant. You reach a dead end, right? So how are we going to solve that? Well, we're going to learn some multivariable calculus, and that'll allow us to get our hands on that kind of thing. Now, again, this is just the low-hanging fruit. These are the obvious, sort of easiest, most immediate examples. The world is full of examples where you really need to take a multivariable approach, and single variable calculus just won't cut it. Okay, now, depending on your field of study, I thought I'd point out some applications and, just broad strokes. Some of y'all might be econ majors, for example. So why does an econ major need to know multivariable calculus? Well, here's a scenario. Let's suppose you have various economic variables, and I just made up some letters that I seem to recall made appearances in my econ classes back in college. This is not a real econ example. This is just kind of a made-up thing. But this is representative of the kind of stuff econ people do. Various variables related by some equation. Very often this is how econ sort of goes. You don't write P equals stuff. What you do is you write down a bunch of terms that represent either quantities or aspects of quantities that sort of add up in a certain way. Like, this might mean something, and that means something, and that means something, et cetera, et cetera. And for, reasons based on a model that you can argue, you can say, those things, they have to add up to zero. So this is what an economic model looks like. It's typically an equation involving a bunch of variables, none of which are solved for. So, all right, given that, suppose you know how some of those variables are changing. How does the remaining variable change as a result? With the understanding that, of course, this equation always has to be satisfied. Right? So if you change L, K, Q, and I, and you leave P the same, the equation's not going to work anymore. Right? If you change L, K, Q, and I, you're going to have to fiddle with P to get the equation to continue to balance, as it must, according to your model. So, again, as these things change, how fast does P have to change as a result? Well, again, single variable calculus, does not do a good job on this question, and multivariable calculus is what's necessary. And so we'll talk about how to answer questions like this. This is an example of a technique that's literally on our course syllabus. Now, before I go on, I want to point out there is something really interesting about this example. Notice we're just talking about economics here. We're not doing theoretical physics. We're not doing relativistic cosmology. This is not a science fiction movie, right? And yet, check it out. We have what I'm going to call 5 + 1 variables here. This math is taking place in what you might call 6 dimensions, which is a scary thought, right? Can we even visualize? Is there a 6th dimension? What does that even mean? Well, yeah, look, it's just math. I'm not saying that there are 6 physical dimensions. I don't even really particularly care if there are 6 physical dimensions. We are trying to understand an equation which involves 6 variables, though. So we are doing high-dimensional math. Even though we're not doing, again, the typically sort of thought of as, creepy sci-fi, ivory tower abstract kind of stuff. This is just econ, right? So, I want to dispel this misunderstanding, very common misunderstanding, that 3 dimensions is all you need because we live in a 3-dimensional universe. That's nonsense. The obvious, easy counterexample, right? So now here's the good news for y'all. I am very aware that it's very difficult to think in, beyond 3 dimensions. In fact, I don't really quite 100% believe anyone can really do it, right? Anytime I find myself when I'm dealing with 4 dimensions, I have to kind of make up little fibs that I tell myself and try to eliminate a variable whatever way I can, right, to try to turn it into something 3-dimensional that we can then kind of, our brains work with 3 dimensions, right? So I'm not suggesting that you're going to develop the ability to geometrically see in 6 dimensions. Absolutely not. You never will. Don't even try. 3 is going to be hard enough. Right? So in practice, when we are doing examples that do involve drawing pictures and visualizing 3 dimensions only, we are reasonable people. Okay, let me pause there for a second. Who's got a question for me? Anybody? Feel free. By the way, while we're paused, I will point out. I'm aware that I talk a lot, right? That's kind of my job, but nevertheless, it is hard to squeeze a word in while I'm doing my thing. So I encourage you to, if you have a question, y'all have read the whole bit that I have on the website about questions, right? What's a classroom question? What's an office hours question? But if you have a good classroom question, shoot a hand up, right? No problem. I might point at you and say, okay, give me 3 seconds, and then finish my thought, and then come back to you or something like that. But please do feel free. Okay, let's look at some other stuff here. Here are some equations that some of y'all might have seen before in some context or another. If you are physics majors or engineering majors, you will see these equations quite a bit. They're a big deal. This is called Maxwell's equations. 2 different versions of Maxwell's equations. So there's a lot that kind of comes up naturally. What does this mean? What's that telling me? Okay, well, look, if you're an engineer or a physicist, you need to know what that means. Of course you do, right? And even just specifically, what's that thing? Right? Now, y'all have seen integrals before. You probably haven't seen 2 integral symbols right next to each other before. Don't worry, we'll get to that, right? But what you probably have not seen is a differential like this with a little arrow hat over it. What in the world does that mean, right? Well, we are going to understand that. after the end of this class. And likewise, the rest of this, all the rest of that. Here's another one. How can you best understand, for example, this statement? It's one thing to know what it's saying. It's another thing to know why it's true, or at least to have a good sense for why this is a natural thing to expect, to have a good intuition for why it's true. Don't just take it on my authority, right? You should take it as a goal to understand why this is true, or at least why it should be true. And that's another thing that we're going to focus on a lot in this class. And again, I remind you, you're going to hear me say this a million times. This is a course about ideas. You can't just memorize this formula, right? We need to understand the related ideas here. And then another thing. Okay, fine. So maybe at some point we know what these things mean. We know what this statement is saying. We know why it's true. Okay, what does that help me understand about electric fields? Right? Well, that's also really, really important for a physicist or an engineer, chemist, arguably, depending. Is how do you make inferences, from cool mathematical statements like this? What does this tell you about the nature of the physical world? So that's another thing that we're going to give a little of attention to. Now, I will point out, this is a math class. It's not a physics class. I do some physics in this class, largely in service of the math. In other words, to show you how the math is useful, and to show you how I claim, in some cases, and these are actually really good examples, the physical world, this thing that we live in, is a useful metaphor for helping you understand math. So we usually go the other way around. Usually math is a tool to understand the physical world. I'm saying the physical world can be a tool for understanding math also. Right, so that's a large part of my motivation to want to talk about this, in addition, of course, to wanting to give you examples. Okay, chem majors out there, perhaps. And again, with the physics majors have a lot of need for this stuff. But chem majors are eventually going to have to understand molecular bonds. Molecular bonds come from the behavior of electrons. Electrons obey Schrodinger's equation. So there you go. If you're a chem major, on some level, you're going to need to understand what this is saying, right? And this is a statement about multivariable calculus in a kind of a hidden way. But this operator right here has multivariable calculus sort of hidden inside of it. So now the good news, I suppose, for y'all is that we are not actually going to do any of this in this course. We're not going to study Schrodinger's equation, but we are going to do some stuff with that. And understanding Schrodinger's equation is something that you can take the ideas that we're going to do in this class and apply. And again, if you're a chem major, when you take PChem, I think y'all will do a little bit of this stuff. And knowing what that means and how it works will help you understand what's going on here. Okay. All right. So that's my pitch. The two big points. I mean, there are the obvious reasons why we clearly need multivariable calculus, right? And then there are these, I like to say, field-specific examples of, economists. So you're going to have a lot of multivariable calculus in your future. Engineers, physicists, chemists, and look, there's a million more examples. These are just the sort of the coolest, most immediate, arguably biggest ones. I'll get it. Overstatement. But anyway, these are some really good examples, but there are many, many more. So here's my my final summary, again, to the question, why are we here? Why are we studying multivariable calculus? Multivariable calculus is the calculus of the real world, where we live. Right? So that's why it's important. It's just, it's in terms of applications, just really, really important. Pausing again. Everybody all right? You buy it? Okay. Okay, so let's get into it then. Now, let's see. I'll remind you first. This course has a prerequisite. The prerequisite course is linear algebra. Okay? And of course, there's a prerequisite trail below that. Y'all read the content syllabus. You know, I'm going to assume that you're good at single variable calculus, Calc 1 and 2, integrals especially, etc. Definitions of integrals, Riemann sums, really important. Make sure you're good with Riemann sums. Techniques, obviously. So linear algebra. So chapter 1 has a lot of stuff in it that really, frankly, is linear algebra, and you should have already seen. So I'm going to do a lot of skipping over stuff that's in chapter 1. Not 100%, because I know that some of what's in chapter 1 you haven't seen. And I know that which you have seen, you might not have retained perfectly. I'm going to remind you, though, that, again, per the recording that y'all watched that I sent over the weekend, I have to make these tough choices. There's just not enough time. There's not enough time. You can't possibly cover everything, right? And so stuff you've seen before, or stuff that follows pretty quickly from stuff you've seen before, it's a pretty natural choice to go quickly, at least, through. So heads up about that. I do start with section 1.6, you're going to notice. 1.6 really is very largely just linear algebra. So let me hit some quickie points on this. There's the triangle inequality, which, again, you might not have seen in linear algebra, but it needs to get said. The triangle inequality is called that because, of course, this is a triangle that represents what this is saying. The magnitude of this A vector is that distance, and the magnitude of the B vector is that distance, and the magnitude of the sum is that distance. So really, all the triangle inequality is saying is that blue plus red is greater than purple. It's pretty clear. I mean, we all know the shortest distance between 2 points is a straight line. That pretty much says this. So, this needs to get said. Okay. All right. How does matrix vector multiplication work? I know y'all know how to multiply a matrix times a vector. What I'm not sure of is if you know all of the ways to think about how to multiply a matrix times a vector. And this is the one that is, I don't want to say it's the least well understood, but if you look at the combination of least well understood and most important to multivariable calculus, I think this is my nomination. This does get used quite a bit, and it's undersold, I think, in linear algebra classes. So in particular, a matrix vector product is a linear combination, like so. Now, a lot of people think of a matrix vector product as, well, you compute a bunch of dot products. Okay, yeah, sure, right, fine, yes, but different point of view, it's a linear combination. And specifically, it's a linear combination of the columns of the matrix. Right? And even more specifically, it's a linear combination of the columns of the matrix where we use the coordinates of the vector as the coefficients in that linear combination. So, really nice fact. And again, this being early in the semester, I'll go ahead and point out another example of what I mean when I say we're not interested in answers, we're interested in ideas. Right? So yeah, you can compute the same result with dot products, one row at a time. We're not interested in the answer. Who cares about the answer? Marginal at best. Right? So what we have here is an idea that does not immediately, obviously, connect to that dot product point of view. So this is a useful idea. There will be times where we're interested specifically in the column vectors. Oh, okay, well, wow, if we know something or are interested in the column vectors, And if we know something or are interested in this matrix vector product, then the fact that there's this huge relationship between them by way of linear combinations, that's a useful idea. That might be the foot in the door that lets us solve a problem. Right? So the fact that it's arithmetically more convenient to compute with dot products, who cares? Not the point. Is everybody on board? Is that cool? Yeah. All right. Okay, if I can, there we go. Okay, linearity. Now, I know that y'all have seen this before. Experience tells me that while y'all have definitely seen this before, a lot of y'all might have seen this early enough in your linear algebra class that you kind of saw it and blew it off, and then got real heavy into matrix manipulations, right? Various kinds of algorithms and procedures and stuff. But it's really important to make sure that you retain and have a strong understanding of the idea, the fundamental idea of what is linearity. And short version is linearity is this equation right here. And I like to say this as linearity means that when you do a linear combination of inputs to the function, you effectively get that same linear combination of the outputs from that function. Some people say linear functions or linear transformations commute with linear combinations. It doesn't matter which order you do the linear combination first, do the linear combination last, whatever. Right? So that's just how we write it down mathematically. So a good thing to make sure you know. Equivalently, you can think of this as two separate facts that linear transformations commute with scalar multiplication, or linear transformations commute with addition. You can think of it as two separate properties. Suit yourself. Okay, and it doesn't matter how many vectors. Yeah. Okay. So hopefully you'll recall all of that. Hopefully you also will recall at least some of these examples from linear algebra class. So this fact right here is sometimes, abbreviated, streamlined by the statement, dot products are linear. So let's think about, why would we call this dot products are linear? Well, if you look at what P does, right? P says, whatever vector X you give me, I'm gonna dot it with this vector A, and of course A is given and fixed and doesn't change. So to a given input, to a function X, right? P is the act of doing a dot product. So when we say P is linear, kind of a reasonable take. You're saying that the act of doing a dot product is linear. Okay. So common lingo for an important statement. Again, make sure that you're good with why this is true. By the way, are you sure that this is true? Do you believe that this is true? Don't just trust me, right? I might be confused. I might be wrong. I might be a scam artist. Who knows? Right? How do you know this is true? Well, this is something you can prove. This is all you got to do is take this formula for this function called P that we're claiming is linear. Just take that formula and come up here and see does it in fact satisfy that equation. And it's just a matter of sort of writing it down and recalling that you already know certain critical facts about dot products. Again, from linear algebra class, you know that dot products distribute, right? And you know that dot products are what I like to call scalar associative. Right? That's old news. You can look back into your linear algebra notes, and so these fundamental properties of dot products are already there. And then persuade yourself by doing the algebra that indeed this property holds. And thus this function is linear. So I think it's a really healthy exercise, and I want to encourage y'all to all give that a shot. A couple of things, related notes, again, taking a pause on the math. I'll do this sort of thing a lot in class, where I will point out, hey, that's a good little calculation. Y'all should do that, right? And you don't have to, but I do think that those are a good investment of your time. It's good practice for exams. For whatever it's worth, when I make those little observations, that's an insight into my mind of, hey, what do I think is really cool? And for whatever it's worth, when I write my exams, very often I'm kind of thinking to myself, hey, what's really cool? Right? So by pure coincidence, I don't do it on purpose, but by pure coincidence, on several occasions, things that I have pointed to in class and said, hey, that's a good exercise, y'all should give that a shot, have shown up on exams. So if only as a strategic choice, you might really ought to consider taking the time to do those exercises. Okay. Likewise, cross products are linear, and a very similar speech. I'm not going to repeat the very similar speech, but cross products are linear. A little bit more surprising, a little bit weirder, a little bit less expected, but it's true. And again, easily proved. Good exercise. Give it a shot. Oh, I should also point out, again, when I make these little suggestions, I do think it's a healthy thing for everybody to try it on their own first. But if you get stuck, don't just sit there and beat your head up against a brick wall, right? You've got a lot of different resources for getting help. I think it's a great idea to try to make use of classmates, study buddies, study groups, whatever. Doesn't even have to be someone in this specific section. Doesn't even have to be someone in my sections, right? There is one other section taught by someone else. Anyone taking the course would be a good person to say, hey, I'm having trouble with this. Let's roll. Do you know how to do this? Oh, you do? Cool, show me. Oh, you don't? Oh, well, we should probably work on this together. So I strongly encourage that kind of thing. I also encourage, if you can't figure it out, even between you and whoever you're working with, then really good idea to seek out other help. So you have several options. There's the help room, right? The help room, no appointment necessary. It's open for I've forgotten, 9 hours a week at times when hopefully as few students as possible have conflicts. So just walk on in there and you can get all the help you need. And of course, my office hours. You're very welcome to come into office hours. I really like it when students come to my office hours and ask me how to do questions that I've suggested. Right? So I'm very happy to help, but you got to actually come and ask. So anyway, keep that in mind. Oh, and then of course the other instructor, I really should find out how to pronounce his name. If you want to go to his office hours instead of mine, perfectly fine. We're going to have a reciprocal office hour sharing arrangement, so you're welcome to go to their office hours too. Okay. All right. This one's a little weird. It almost looks like I'm saying determinant is linear. But that is, however, not what this is saying. Very importantly, determinant is not linear. After all, determinant takes as its input a matrix. And if you add two matrices, their determinants do not add as a rule. Okay, so very importantly, we're not saying here that determinant is linear. What I'm saying is that this function I'm defining that makes use of determinant is linear. So in particular, D, that's the thing that I'm claiming is linear. D, you'll notice, it does not say, you give me a matrix, I give you a number. D says something different. D says, you give me just a single vector x. And And apparently then this is what happens to x. So in order to execute this function called d, I need to know these several other vectors that have to be given, that in combination with x will in fact make a matrix which I can then take a determinant of, right? So this is not matrix in, determinant out. This is vector in, then combined with various other vectors to make a matrix which you then take a determinant of. So very different than the determinant function. Everybody see the difference between d and determinant? Okay. So my claim is that d is linear. That's a really important fact to know. So this goes by different names. I like the classical term. This is called multilinearity of determinant. Multilinearity is a reference to the fact that not only do you get linearity when you put the input vector in the bottom row, it also works in any of the rows. And it also works in any of the columns. You can state similarly. So multilinearity, kind of a natural term there. Okay. So you might think back to what you know about how determinants relate to row operations, and you can persuade yourself from that pretty quickly that this is in fact linear. So good thing to think about, yeah.
So if we're writing something or proving something on a test or a homework question, is it fine just to write because of the multilinearity of determinants? Therefore...
Yeah. Oh, yeah. No, I'm very happy for you to. I'm very happy to assume multilinearity as prerequisite material. Yeah, totally.
Okay.
Yep. All good. Anybody else? All right. Moving along. Other cool facts about linear algebra. I mentioned this one not because I don't think you've seen it, but because, again, like linearity, it's really important. Super duper duper important. A lot of the applications that we're going to do with linear algebra in this course come from this theorem and its resulting proof. Linear transformations. Right? T there is a linear transformation. Linear transformations are matrices, and matrices are linear transformations. Really important fact. Now, yeah, asterisk, and I was careful to put this in the statement. When I say linear transformations, I'm talking about what I like to call Euclidean linear transformations. So Rn is the input space, Rm is the output space, right? So I don't want to talk about linear transformations on vector spaces of functions, stuff like that. So yeah, that's different. But Euclidean linear transformations are matrices. Okay, so now why is this true? Well, if you give me a matrix that you then use to define a function in this way, it's not that hard to just plug it into the definition of linearity and confirm that this is in fact a linear transformation. That's plug and chug. Y'all can totally do that yourselves. It is trickier the other way, quite tricky, if you have a function that you know is given to be linear. How do you conclude? That's a bad question mark. Let me try that again. How do you conclude that there's a matrix like this that makes this thing work? Right? How do I know that that's where am I going to get this matrix? I wasn't given a matrix. Do I have to make it up? Right? How do we know there is such a matrix? Well, yes, we are going to make this matrix. We're going to make it ourselves by a brilliant but standard little trick. And my favorite observation about this argument is that you do not have to have made it up on your own. You are allowed, as we all are, to copy off of previous mathematicians, right, who have done the brilliant, insightful, creative thinking for us, right? And the brilliant idea is this right here. That idea right there is that you let the columns of the matrix, this matrix that we have to find, just let its columns be the outputs from our given linear transformation. These are sometimes called images. The images of the standard basis vectors, and I hope you all recall standard basis vectors. It's like IJK, but I don't want to risk, again, I don't want to tie my hands to only 3 dimensions. So we use E1, E2, E3, etc. through En to represent basically IJK, but in dimensions. So the columns are the images of the standard basis vectors. Brilliant idea. You make that one choice, and everything just kind of falls into place. And here's the calculation. So, having made that choice, let's see, apparently I need to compute T of x and make sure that T of x is what it's supposed to be. Namely, I have to make sure that T of x actually is AX. All right, well, linearity allows me to take a inside linear combination and turn it into an outside linear combination. And this little brilliant insight allows me to rewrite that as that. And then notice here I have a linear combination of columns. Where have we heard that phrase before? Linear combination of columns.
Product.
Yeah, that's right. And that is as it's supposed to be. That is the product AX. And so as required, T of x is AX. And that's how we know that this little slick little move right here, let the columns of your matrix be the images of the standard basis vectors. That's how we know that this slick move makes the linear transformation work. Is that cool? Okay. All right, so let me tell you how you're going to use this in a lot of cases. Y'all will recall from the talk that I recorded and sent this weekend that I was talking about how, there's prerequisites that we're going to use a lot. Certain parts of linear algebra that are just really important to make sure that you're good on. And one of those was how to write a matrix that executes, for example, a rotation. How to write a matrix that executes a reflection. Something like that, right, in R2 or R3. Okay, well, here's how you do it. If I'm going to talk about, let's say, a rotation, apparently all I have to do is look at just the standard basis vectors, rotate them, see what you get, and whatever you get, those are the columns, and bam, there's your matrix. That's how you make a rotation matrix. You just follow this prescription. Take all your standard basis vectors, do whatever the geometric process is that you're trying to write down as a matrix, make those your columns, declare victory. Okay. Everybody happy? So play around with that. Make sure that you're good with that. If you have trouble, office hours. Right? Come talk to me. Happy to help. And help room and classmates, et cetera, of course, right? But seek out help and make sure you're good to go with that stuff. All righty. Okay, now this I'm going to throw a couple of minutes at or less. I just think this is underappreciated in linear algebra classes, and that is that this idea of matrix multiplication. And again, a lot of y'all have seen matrix multiplication. Well, you've all seen matrix multiplication. And very often it's presented as this weird little formula where you compute elements of the product, one element at a time, with this sort of odd choice of dot this row with that column. It's very arbitrary and strange seeming and like, okay, I guess, but why? Why are we doing that? Who dreamed that up, and what was that person thinking? Well, here's what I think is a really crisp answer to the question, because when you do that weird formula, with dot products, rows and columns and stuff. Then when you have a couple of linear transformations, effectively the act of multiplying the matrix in effect composes the linear transformations. It's like taking the outputs from the first transformation and plugging those outputs into the second transformation. And that is a fundamentally natural mathematical thing, right? Taking functions and Legoing them together, right? What comes out of one goes into the next. Composition is matrix multiplication. So that's my crisp answer to why do we do matrix multiplication like we do? It's because of this natural connection. So anyway, again, I think that needs to get said. Okay. I tell you what, just for my own curiosity, how many people knew this already? Show of hands. Not many. Okay. All right. So good for y'all who did, but I think it's worth mentioning because so many students just don't get to see that. Okay. So that's section 1.6. Reminder, the way homework works in this class is when we get to the end of a book section, I will put it on the lecture schedule, which anyway, you all have seen the lecture schedule. But I will enter it on the lecture schedule, and whatever exercises are on the content syllabus corresponding to those listed sections, that's what the homework is. And so we have just finished with section 1.6. We now officially have homework for this week. And anyway. Okay, a couple of real quick things I want to say about section 1.1. This is ultra quick, and then we'll go on to 1.2. Most of this y'all have seen before. So again, time is tight. I'm not going to repeat a bunch of stuff you've already seen. Man, there's a lot of ideas in Chapter 7 that really need class time, so I can't waste it on stuff like this that's easy and in your past. So I will point out, our book and many others uses bold as the sort of accent to indicate that a letter of the alphabet represents a vector. I think that's a weird choice, because we can't do it very easily with a pen or pencil. I mean, nobody's going to sit there and, come on, this is silly. So it's kind of a jerky choice in that sense, right? So I like the vector hat because it's easy to do with handwriting. And in my documents that I produce, I always use the vector hat and never the bold for that reason. Okay, so heads up on that. Here's another little gripe, quibble, pet peeve, whatever you want to call it. How do you represent this vector right here? Given those points P1 and P2, how should we represent that vector? A lot of books will write it as like this, P1, P2. I would prefer to write it as P2 minus P1. After all, keep in mind how vector addition works. There's P2, which is a point, but thought of as a vector. Here's P1, which is a point, but interpreting it as a vector, the canonical way. And check it out. Sure enough, this green thing literally is P2 minus P1. So let's look at these two options then, right? We can write that green vector either like this or like this. Which do we like better? Pros and cons. The advantage of this right here is that it has fewer pencil strokes. You're going to save ink. Right? That's worth a little something. I think this is way better. This visibly shows an algebraic relationship. Algebra is our friend. Algebra is the tool by which we solve problems. Why would I want to hide the algebraic relationship? I don't want to hide algebraic relationships. I want to emphasize algebraic relationships. So I've always kind of, dare I say, resented this notation. I think it's a bad choice. I don't like it. You'll never catch me doing it without me simultaneously mocking it. I just don't see the purpose. Anyway, now you can if you want. I'm not trying to, tell you can't do it, but I think there's a lot to be said for this right here. Okay. All right, that's my presentation on 1.1. Let's see. Oh, and are we out of time? Is that kind of perfect? Let's see here. Oh, I've got a phone. We are indeed out of time. Okay, so we will draw the line right here. We'll pick up there on Wednesday. Nice to meet y'all. Have a good rest of your day. See you later.